Thank you, Rohsenow, for the introduction, and thank you, Mattel, for inviting me to present my work at the Thermal Transport Cafe. So when Mattel first invited me to give a talk, I was a little bit hesitant because a lot has happened to me during the pandemic. I got a new job, I moved to a new city, I had a new lab, and I started a new family, with new kids. And I even bought a new house this year. But on the research front, not so many new results. So I apologize in advance if you find some of my, most of my slides look suspiciously familiar. But again, this is boiling we're talking about. It's not exactly the old will become the new again, per se, but from time to time, you might derive new meanings or new insights from old data. So I think before I start, it's almost like a tradition to first say a few words about myself. I received my bachelor and a PhD degree from Shanghai University. And actually during my PhD study, I spent 1 year at the University of Tsukuba in 2010. And at the time I was a research student trying to measure the second sound in superfluid helium. And the emphasis is on the word trying. That was not very successful effort, but I took a very strong liking to the Japanese culture and its people, and so much so that after graduating from Shanghai University, when I learned there was a job opening at Professors Yasuyuki-Takada's lab at the Kyushu University, I jumped on the opportunity without any hesitation. Even though I knew very little about Boiling heat transfer, I hadn't done any actually two-phase flow research at that point. And after that, I was promoted to assistant professor in 2018, and I moved to University of Tsukuba in 2020. So it's really a kind of a life cycle for me to return to the point first I started. Okay, about the university. University of Tsukuba was formerly the Tokyo University of Education. As you can imagine, the university is very passionate about education, and not just a college level education, but all kinds of education. As a matter of fact, the affiliate high school of University of Tsukuba is one of the top high schools in the country. Early this year, there was this big news about the Crown Prince of Japan was going to attend the affiliate high school of University of Tsukuba in April. And that was the first time for any any member of the royal family to attend a public school. And actually, it's way more difficult to get into the affiliate high school of University of Tsukuba than the university itself. And the university was established in 1973, which means next year it's going to celebrate its 50th anniversary, and it's located in Tsukuba Science City, which is about 50 kilometers northeast of Tokyo. And if you take the Tsukuba Express rapid train, it only takes about 45 minutes to reach downtown Tokyo. So it's very convenient if you happen to visit Japan. Yeah. And the history of the city itself is kind of intertwined with the university. So in the 1960s, Tokyo already had this problem with overcrowding, and the government tried to move some of these resources out of the city and build the science city. And at the center of the city will be a new type of national university, where the power center will be moved from the professors to the administrators. And that university will later become the University of Tsukuba, and the city will, of course, be the science city of Tsukuba. And now, after almost half a century, the city has become these, how to describe it, a kind of a scientific hub of Japan. And it's host to over 60 national research institutes and 240 private research institutes, which the list includes AIST, National Institute of Advanced Industrial Science and Technology, NIMS, National Institute of Materials and Chemical Research, and of course, JAXA, the Japanese version of NASA, and the 𝗘𝗵, the famous high energy accelerator research organization. And over the past couple of decades, almost half of the public research budget of the whole country is spent in Tsukuba. And over 10% of the population of the city holds post-college graduate degrees. And as you can imagine, the medium income, the medium household income of Tsukuba is very high. So just to give you an example, like my neighbors drive very expensive foreign cars like a BMW and Tesla, and I have 2 bicycles. So there's that. And the University of Tsukuba is ranked 9th in Japan and 219th worldwide. And it has a student body of about 16,000. And it has a faculty about 5,000 strong. And over 10% of the student body actually international students, which makes University of Tsukuba one of the most international universities in Japan. And it has produced 3 Nobel laureates, like Professor Tomonaka Shinichiro and Professor 𝗪𝗏𝗄𝗏 and Professor Shirakawa Hideki. But university is actually more famous for its long tradition in sports, like these Jigoro Kano, the father of judo, served as president of the university for 20 years. And it has sent over 70 students, athletes to the Olympics over the years. All right, let's go back to the main topic of today, which has to do with Boiling heat transfer enhancement. Specifically, I'm going to talk about 3 separate studies of how boiling can be enhanced using surface wettability engineering, or more precisely, a combination of wettability engineering and the topographical modifications of the surface. And lastly, since Mattel always asks for new ideas, I'm going to offer some of my, how to say, like immature or sophomoric musings about the current state of boiling heat transfer research and the direction the research might go in the future. So let's first go back in time. So here's a plot of the number of publications, actually boiling related publication versus time in the Web Science Core collection. So in almost every textbook on heat transfer, the beginning of boiling heat transfer research is attributed to Nukiyama's description of the boiling curve in 1934. Here I want to dig a little bit deeper. I don't know how many of you have actually read the original paper by Nukiyama, which is actually a terrific read. So it was written in the very, very old-fashioned style. And for better or for worse, not so many people write papers like that anymore. And after reading the paper, I learned a couple of things. First, Nukiyama didn't measure the whole boiling curve. because he couldn't control the surface temperature, the part about the transient boiling was actually missing from his data. And second, he never used the term like critical heat flux in his paper, which makes me wonder who actually coined the term critical heat flux. If you know the answer, please let me know. And thirdly, he's very honest about limitation of his experimental setup. A big chunk of the paper was actually devoted to uncertainty analysis. And right out of the gate, he acknowledged the impossible task of theoretical boiling phenomena. So he wrote, I quote, "As the boiling phenomenon is so involved and complicated, the analysis of boiling heat transfer is almost an impossible problem." And finally, he cited only 5 papers. So I guess you know you're the pioneer of any field if your paper only contained 5 references. So after the groundbreaking work by Nukiyama in the 1940s and the 50s, nothing actually happened. That is the case until another groundbreaking work came onto the stage, and that is Zuber's hydrodynamic interpretation of boiling phenomenon. And that really elevated boiling from engineering curiosity to a serious scientific topic, and putting boiling on the map, so to speak. And around the turn of the century, the world has seen another wave of, or another golden age for boiling research. And this time, it was not driven by any particular theoretical work, but by a sudden proliferation of all kinds of toys or tools at our disposal to directly manipulate and control surface properties. And there is now a global contest to see who can come up with a boiling surface that has the highest, that can have the highest CHF, lowest OMB, and can last forever. And my work is pretty much part of that effort. And the one surface property I'm focusing on is surface wettability. I don't think I need to explain how surface wettability works to this audience. So on the left, you have the column for hydrophilicity. So here, the surface is actually a titanium dioxide surface under ultraviolet irradiation. So the incoming photon can knock off like an oxygen atom from the surface, thus creating vacancy in the surface that can help the surface to bond with water or hydrogen atoms in this case. So the surface has a very, very high CHF and also a minimum heat flux MHF. And that means the surface works very well in the high heat flux region. So at the opposite end of the spectrum, you would have a hydrophobic surface. And here is an example. I think this is a copper. This may be a copper surface electroplated with a very thin layer of suspended PTFE particles. And the surface has a very high contact angle, maybe reaching 140 degrees, but it has some kind of durability issue, but that's another story. Anyway, the surface has a very, very low onset nuclear boiling, but once boiling started on such a surface, it was soon turned into this very thin vapor layer, which makes the surface pretty much useless for any heat transfer application. But not all hopes are lost when it comes to hydrophobic coating. When combined with hydrophilic substrate, it can work pretty well. And the end result is what we call a biphilic surface. It's a surface with alternating hydrogenous pattern of hydrophobicity and hydrophilicity. And as you can see here, you can have heat transfer enhancement from OMB all the way to CHF. And more interestingly, you can have these very ordered bubble nucleation and growth on the surface. The bubbles tend to form on the hydrophobic part of the surface, but their expansion on the surface will be limited by the surrounding hydrophilic area. And it will be remiss on my part not to mention this new concept, the para-hydrophobicity, which entails both high counter-angle and high counter-angle hysteresis. So here's an example of a para-hydrophobic surface, and it mimics rose petal instead of lotus leaf. And boiling on such surface tend to have both low OMB and a high CHF. And if you pay attention to how bubbles grow on such a surface, as you can see here, the footprint of bubble tend to be very small, which means its expansion on the surface has been greatly hindered, which makes it work in a very similar way as a biphilic surface. So I guess the key here is trying to come up with to directly control contact line dynamics on the surface. All right, let's start with the case of enhancement of subcooled boiling. This is the first project I did since joining the University of Kyushu. And I want to thank Professor Takada and all the students working on this project at that time, who definitely knew more about boiling heat transfer than I did. And thanks to all their, thanks to their teachings, really, I get to learn how to do boiling research. So as I mentioned before, also nuclear boiling tends to be very, very low on hydrophobic surface, but that is not the conclusion you can draw from a theoretical modeling. According to classical heterogeneous bubble nucleation model, bubble only emerge from embedded vapor embryo in the surface when the surface superheat reach a value that is a function of the saturation temperature, surface tension, the density of the vapor, latent heat vaporization, and the cavity size. As you can see here, it has nothing to do with surface wettability. And apparently that is not the case. We have direct experimental data showing that there is a very strong nonlinear dependence of OMB superheat and surface contact angle. So I think that the surface used in this study is ultra smooth glass substrate and graph coated with self-assembling monolayers of different wettability. So you can have these so you can almost remove surface roughness as a parameter and focus on the surface contact angle. Anyway, so as you can see here, as the contact angle increases, you tend to have very low onset nuclear boiling superheat. But the question is how low? Based on our subcooled boiling experiment, the number can be pretty low. Actually, as you can see here, after coating the surface with hydrophobic PDFE spots, under 20 degrees subcooling, the onset nuclear boiling actually enter negative territory. And it's actually very easy to come up with explanation. The culprit, of course, is the dissolved gas in the water. And after switching to a closed system boiling setup, and these negative onset nuclear boiling pretty much disappear, and along with it, the heat transfer enhancement in the low to intermediate heat flux region. And that is not the most interesting part. What is interesting about this research is that none of this behavior can occur with homogeneous copper surface. As you can see here, with the same experimental procedure and setup, and you don't see this kind of dramatic change in the boiling curve. And that means the hydrophobic part of the surface has this unusually strong affinity for vapor or gas. And such a strong affinity can also be found in the way bubble departs from the surface. So in subcooled boiling, bubble growth is depends on the balance between the evaporation at the bottom and the condensation near the bubble cap. And as you can see here in the closed system, the bubble pretty much just stay on the surface without departing because the condensation was too strong in this case. It kind of suppressed a bubble departure. But in comparison, in the open system, and the high gas content is enough to weaken the condensation to a point where the bubble size can grow large enough for buoyancy force to overcome whatever is holding the bubble back on the surface and carry it off the surface. And we run some diffuse interface simulation using a water nitrogen system, and we observed pretty much the same behavior. That is like you tend to have a bubble departure from the surface only if you have also a high concentration of dissolved gas in the liquid phase. So after this initial success with subcooled boiling, we move on to a more challenging situation involving low pressure boiling. And boiling heat transfer is very sensitive to pressure change. As you can see here, the boiling curve for a copper surface will shift to the right. That means you will have a significant heat transfer deterioration. And as you can see here, boiling no longer works in a continuous mode under low pressure. Instead, you will have this sudden burst of a giant bubble from the surface from time to time, and the surface can stay quiet for a very long time. That's very bad for any heat transfer applications, of course. And then we tried the same experiment with a copper surface, I think coated with nichrome TFEO, maybe particles in this case. And the results show very dramatic difference. The boiling curve almost immune to the pressure change. And as you can see here, like most of the nucleation sites remain active even under such a low pressure. But like any good stories where there's always a plot twist at the end, the pressure resistance of the biphilic boiling surface, I can only say it's too good to be true. It was later found that when the pressure is further reduced, a sudden transition to this kind of intermittent boiling mode also occurred on the biphilic surface. And so we have to kind of modify our conclusion a little bit. So to reflect that the transition to intermittent boiling was only effectively delayed, but not eliminated on the biphilic surface. And to solve this problem, we need to figure out exactly how that transition happened. And that is exactly what we did. We tried to gather more data on bubble dynamics from a single hydrophobic spot. So the first thing we noticed is that at high pressure, you can always have this vapor residual left on the surface after bubble departing, after bubble departure. And like it's easy to imagine that for that to happen, the contact line has to be affixed to the surface in the final moments leading up to bubble departure. So the bubble, the rupture of the bubble interface happen in the middle of the bubble instead of at the bottom of the bubble. And this remaining vapor on the surface is critical because you can, like from these residual vapors, you can start the next cycle bubble growth without any delay. And that's very good for heat transfer applications. And by comparison, at the low surface, at the low pressure, and the amount of vapor residuals tend to be significantly less. And from time to time, you have these clean bubble departure from the surface. That didn't happen at the high pressures. And without vapor residuals on the surface, so in order to start the next ebullition cycle, you have to wait maybe seconds, like in this case. And that's how the intermittent boiling mode starts to take over even on the biphilic surface. And now we have these experimental observation. The next step is to figure out exactly what happened. As I mentioned before, the existence of bubble residue on the surface has a lot to do with how contact line move in the final moments leading up to bubble departure. So in the case of low pressure, our hypothesis is that the contact line somehow became dipping from its original position on the surface, and that causes this disappearance of bubble residue from the surface. And it turns out the way contact line move on the surface is not a trivial matter. It has a subtle but significant impact on bubble departure itself. So on the left, you have these experimental data on bubble departure diameter as a function of pressure. And let's consider a scenario where the contact line remain fixed or ping on the surface somehow. And the bubble departure will depend on the force balance between the buoyancy force and the resisting surface tension force. And here is a simple prediction coming out of that model. And as you can see here, the prediction is almost independent of pressure change. And let's consider a second scenario where the contact line is allowed to move in the moment leading up to bubble departure. And that means the bubble base is always shrinking. And in that case, the bubble departure actually depends on the force balance between the buoyancy force and the viscous drag force. And you will have a very different prediction for bubble departure size. And in this case, it's strongly dependent on the pressure. As you can see, the transition between the ping contact line model and the deep contact line model capture this transition of bubble departure diameter we actually measure during in our experiment. And that begs another pesky question: what actually triggers bubble motion? What actually triggers contact line motion on the surface? And the answer is surprisingly simple and straightforward. It has to do with how fast the bubble expands on the surface. So we ran some simulation and just to compare the cases with fast bubble growth and slow bubble growth. And as you can see here, in the case of faster bubble growth, the contact line is is not responding to the changing surface wettability. And but in the case of slow bubble expansion, you have this like a ping contact line throughout the bubble growth process. And the same kind of behavior we also observed in experiment. So here's the experimentally obtained bubble growth data. As you can see here, like in the case of deeping contact line, you will have significantly faster bubble growth. So there's I would not say a direct causation, but there's definitely some kind of a strong correlation between the contact line dynamics and bubble growth dynamics. So knowing how contact line depainting happens gives us some kind of new ideas about how to prevent it from happening. So here's a plot of bubble departure diameter as a function of pressure. Just as before, there is a clear transition from the pin contact line mode to the unpin, to the deeping contact line mode at when the pressure decreases to a very low level. So next, we modify the surface to add dimple cavities on top of the underlying biphilicity pattern, so as to like kind of erase the energy cost of contact line depainting. And compared with the flat biphilic surface, there is definitely definitely a secondary contact line peening effect happening. And apparently, the new surface with the presence of the cavity, a deeping contact line would have a second chance to get reattached to the surface as it recedes deep into the cavity. And such extended pressure range for the pin contact line mode, I have to say, is only marginal. And that is that was confirmed by the heat transfer measurement. As you can see here, like with the dimple biphilicity surface, the heat transfer coefficient show significant heat enhancement for pressure level down to about 9.5 kilopascal. If the pressure goes any further, there's almost, sorry. So there is almost no effect, even with the dimple biphilicity surface. But I will argue this surface enhancement is in the right direction. So the concept might work even better with more elaborate surface structure design, such as re-entrant type cavities. Okay, the last topic I want to cover has to do with the boiling of fluids other than water, and especially low surface tension liquids. As I mentioned before, in the past 2 decades or so, we have seen progress making like leaps and bounds when it comes to surface engineering. Now we have all kinds of enhanced surface design for boiling of refrigerant even. And these surface design include coated surfaces, where you have the enhanced surface structure being coated onto a substrate made of different material. Examples include spray coating of polymer nanofibers, sinter coating of copper microparticles, and opposite such a coated surface, you have these intrinsic surfaces, just like the name entails. Such a surface, with such surface, the enhanced surface structure are directly grown onto the substrate, which leads to zero thermal resistance, thermal contact resistance, and a better bond between the coating layer and the substrate. Example include open cell forms produced by carbonization, privatization, and blowing. And with active manufacturing techniques such as selective laser melting, you can fabricate even like very complicated 3-dimensional structures such as octet-truss unit cells. And of course, you can combine these 2 techniques to make hybrid surfaces. For instance, there are microchannel fins with microparts coating and a 3-dimensional re-entrant type cavities coated with polymer coatings. So there is a common thread connecting all these surfaces, and that is increased surface porosity. And the resulting proliferation of active nucleation sites is believed to be the major driver for the enhancement of boiling heat transfer. By comparison, there has been very few studies devoting to boiling heat transfer enhancement using surface like wettability. And in this work, we start with a porous coated surface, and specifically a thin, highly porous aluminum layer was grown onto a plain aluminum surface using phosphoric acid anodization. And we call this surface a PAA surface. And it has the average pore size about 0.2 microns or 200 nanometers. And we run the boiling test or ethanol boiling experiment to be specific on such a surface, and the results show significant heat transfer enhancement with the porous surface, and it is easy, very easy to see why. And because on the porous surface, you simply have more bubbles being generated. And the funny thing happened the next day when we tried to repeat the experiment. And at this point, the surface has been immersed in ethanol overnight, and it is only reasonable to assume the surface at this point has to be fully wetted. And the results show almost 50 Kelvin jump in terms of onset nuclear boiling. But as you can see here, the boiling curve, the boiling section, the nuclear boiling section of the boiling curve remain the same. So there is a significant delay once the nuclear boiling occurred on the supposedly wet porous texture surfaces. And next enters our hybrid approach, adding wettability engineering on top of like porous texture surfaces. And here we use this polymeric coating with a very long and quite honestly intimidating chemical name to create a biphilic pattern on the surface. And now the PAA surface is partially hydrophobic against even highly wetting ethanol. And we ran the same test, same set of dry wet experiments on the biphilic microporous surface. And the results show even when the surface is supposedly fully wetted, you still have a very low onset nuclear boiling in this case compared to like uncoated microporous surface. There is a 80% reduction in terms of OMB superheat. And we have some tantalizing clues as to how this can happen. As you can see here, the bubbles first appear on the hydrophobic spots on the surface, and it worked as a fuse lighting up the surface pretty fast. As you can see here, if you increase the surface heat flux just by a little bit, now almost all the not all the nucleation sites will suddenly come into life, becoming activated. So the hydrophobic spots were able to provide stable nucleation sites, almost irrespective of the initial wetting state. And we have developed some kind of theory as to how this can happen. Our hypothesis is that on the hydrophobic surface, the bubble nucleation has more to do with pre-existing nanobubbles on the hydrophobic surface, but that's maybe a little bit beyond the scope of this presentation. If you are interested, you can always check out our paper on that topic. So we not only try like a microporous surface, we also try nanoporous surface, and in this case we use sulfuric acid anodization to make nanopores on the surface, and we apply the same biphilic pattern on the surface, and the results show consistent heat transfer enhancement only on the biphilic porous surfaces. So that bring us to the final part of my presentation. So here is my 2 cents about the current state of boiling heat transfer. So as you recall, at the beginning of my presentation, I mentioned like Nukiyama was pretty pessimistic about boiling heat transfer as a topic for theoretical modeling. But I will argue the answer to the question whether or not it is an impossible task to come up with a theoretical model for Boolean heat transfer should be a conditional yes. As you can see, like over the past 50 years, we have developed many heat transfer models for Boolean. So in the case of like isolated bubble stage, that is a low heat flux region, and you have a heat flux partition model covering like heat transfer mechanisms such as transient conduction, natural convection, and of course microlayer evaporation. And it works pretty well as long as you have accurate data on like active bubble nucleation site density, bubble departure frequency, and a diameter. And in the case of fully developed stage, you have complicating factors like vertical and lateral mergent bubbles. But still, there is a way to describe heat transfer as long as you know exactly the vaporization rate, like per bubble stem, like underneath these giant bubble which tend to form on the surface. And when it comes to CHF, like you have like even like almost right from the beginning, you have like all kind of theory, like for instance, Zuber's hydrodynamic theory about the CHF. In his model, CHF occurs when the vapor, when the release vapor reaches the critical velocity to trigger hydrodynamic instability at the vapor-liquid interface. And Koenig focused instead on what happened like parallel to the surface. And his model included very nicely the effect of surface wettability on CHF. And of course, Mattel's latest continuum population model revealed this statistical nature of CHF. So CHF coincides with this maximization of bubble cluster, like footprint area on the surface, which in turn has to do with these triplet critical parameters like nucleation site density and bubble growth period, and of course bubble radius. So we have the heat transfer model for boiling. And what we don't have is this direct link between the boiling surface and the bubble behavior or contact line dynamics. So in other words, we don't have a model that uses surface geometry, structure, or chemistry as inputs and outputs nucleation site density, bubble growth time, bubble release frequency, and the bubble radius. And as long as like if we can figure out how to establish this link between like surface condition and the bubble behavior, I think it's like a boiling heat transfer can be solved in the near future. So as I was researching on this topic, I came across this very nice essay by Linhart, which is written in the 1980s. Of course, he was describing the history associated with Zuber's hydrodynamic CHF model, but I think some of the conclusions still apply to today. And I was particularly struck by the way he described advances or progress made in science. And I quote here, if progress occurs in science, if by revolution and replacement, not by accretion of knowledge. So experts in any field have this like tendency, even knowingly or unknowingly, like resisting new ideas. That is because experts know the subjects too well, and they have this like a tendency to have to put too much confidence on the existing framework of the research. And they tend to believe that if only they had like a more precise measurement, like any problem can be solved. But that is usually not the case. And in my opinion, to move boiling research to a next level, we need some new ideas. And we have to like borrow from other fields, for instance, artificial intelligence maybe, and to invent new tools for Boolean heat transfer. So that's the final slide of my presentation. I want to thank all of my colleagues at the Kyushu University and all the students working on all these projects over the years, and my funding like bodies like JSPS and NEDO of Japan. And here's a list of like all the related publications. Like if you're interested, you can check out for yourself. So that's the end of my presentation. I'm more than happy to take any questions and maybe to have a discussion with you guys. Thank you very much.